Welcome to this LF Energy EVerest video. My name is Robert de Leeuw. I'm Technical Evangelist at Pionix, and in this video we will talk about what's new in OCPP 2.1. With the EVerest community wrapping up the development of OCPP 2.1, the community is now getting ready to implement OCPP 2.1. That meant we started doing an in-depth analysis of OCPP 2.1. We shared that analysis within the EVerest community. But we thought, hey, why keep that internally in the EVerest community? We're an open source project, so let's also share this outside for everybody that's interested in OCPP and what's new in the upcoming release of OCPP 2.1. Now, in this video, we will not go really in depth. We just look at all the new features, all the new use cases that are in OCPP 2.1, but it gives you a good idea of what's coming in the next version of OCPP 2.1. Now, the current state of OCPP 2.1, the first internal review within the Open Charge Alliance started in July this year. That was followed in September by a 60-day public review period. That period has now ended by the end of October. I understand from the technical editors that they got over 500 comments, so they have their work cut out. They will need to do a lot of work to get all of that processed and into the final release. They are still planning to do a final release by the end of January. Now, with the amount of comments, it might be delayed a little bit, but I'm convinced that within Q1, OCPP 2.1 will be released. Now, this video is based on the public drafts, so if you have a version of OCPP 2.1 before you, please compare that. That is the same document that this video is based on. So this is the document that is marked with 1st of September 2024. So basically the public review document that everybody on the internet has access to. If you're looking at this video on a later date, when the final version is out, there might be some differences because things might have changed between the draft and the final version. Now, if you open up the 2.1 documentation, I think the technical editors did an amazing job by marking everything that is new with something that marks them as new with 2.1. So if you look at the new use case, a new message, it is marked with the text new in OCPP 2.1. If there isn't that much space, they might have used just 2.1 between brackets. So you can easily search on either the text new in OCPP 2.1 or you search for 2.1 between brackets and you will find all the new changes. So if you look at, for example, the screenshot I took here from the spec, these are two functional requirements that were already in OCPP 2.1. Both have been updated, so they've been marked as, hey, this is new or updated in 2.1. Now, in this case, it became possible to add ISO 15118-20 certificates. So if you would take both the 2.01 spec and the 2.1 spec, you will see that there's an additional enum value now that can be sent in the trigger message request. So you will need to compare both documents, but it is really marked, so it's really easy to find the differences between the two specs. Now, what's the main reason to do OCPP 2.1? We hear a lot of people complaining about, yeah, but we're still on 1.6. We haven't even implemented 2.01. The main reason is to get V2X support into OCPP. Being able to do vehicle to grid is a promise that we as an EV charging industry have been saying to the world for 10, 15 years already. An EV is just a battery on wheels. They're perfect for balancing the grid. But for that, we need V2X support. Now, that comes from 15118-20. Now, with 15118-20 having been released last year, now it is also possible to release an OCPP version that supports this. So that's the main reason to do OCPP 2.1. There's a way more, and that's also what you will see in this video. There's way more new functionality, but the main reason to do 2.1 is the V2X support. Now, the goal of the committee that is writing OCPP 2.1, so the technology working group of the Open Charge Alliance, is to make it as backwards compatible as possible with 2.0.1. As everybody knows that has been in the industry longer, the step from 1.6 to 2.0.1 is a big one. A lot of stuff has changed. We also knew that there's a reason why it's not called OCPP 1.7. There's a lot of breaking changes. Now, with 2.1 is a small step from 2.0.1. Yes, there's a lot of new functionality, but the core functionality is the same. There's no new use cases in OCPP 2.1 core There are a number of extra requirements, but those are limited, and you can easily find them. So if you have an OCPP 2.1 implementation, you want to make it into a 2.1 implementation, you can quickly go over the spec, look at all the things you need to do to add this to your implementation. That is also what we're now doing at the moment with EVerest, is getting EVerest ready for at least 2.1 core as soon as possible. Now, the committee is also making sure that backwards compatibility is as easy as possible. So we try not to change messages where they are not really needed. If you compile the schema files, you will find there's 2 changes in existing fields. 2 fields went from optional to required. So if you had an implementation and you didn't use these fields, now you will have to. But as these fields were optional, you could already have had an implementation that was using these fields anyhow. And you wouldn't even have to do anything to make your implementation backwards or forwards compatible with 2.1. Now, if you would do a 2.1 implementation, as these fields were optional in 2.0.1, it means it will still work with 2.0.1 because those fields were already there. They just became required now. That's the biggest changes to existing functionality there. Now, if you then look at really functional use cases that are added, yeah, we need to support -20. Now, -20 brings a bit more than just V2X. All the certificates are different. There is now multiple root CA supported in -20, and for that, new certificates need to be able to be installed in a charging station. I don't know the exact details what's different within the certificates themselves. I haven't looked at that much detail yet, but there is now a way to ask the charging station to install a -20 certificate because it's different from a -2.1. There's new smart charging use cases coming with -20. -20 allows something called scheduled control mode and dynamic control mode. With the scheduled control mode, the EVZ gets a set of charging profiles. So you can send 1 up to 3 charging profiles to a vehicle, and then the vehicle will decide, depending on parameters it has, depending on some criteria, which schedule it will use. Now, every schedule can have a tariff, so it can be based on price, it can be based on green energy, can be based on I need to leave early, that the vehicle selects a certain schedule. The other alternative is dynamic control mode. That's where the EV, when it connects to the charging station, will tell the charging station, hey, these are my requirements. This is the fastest I can do. So this is the fastest schedule I could do. So taking into account battery heating, the connection, the cable, all of the information that the vehicle has to come up with a schedule. This is the fastest I can do. And then the charging station comes back. Okay, then I can give you this option to make that fastest schedule. Now, if you have either of these new control modes, things change. Maybe there's less energy available. Maybe the car needs more energy because it wants to leave faster. K20 defines how to do that. So how to change the selected schedule after charging has started. So K18 and 19 are really the start of the smart charging schedule. K20 is how do you change that in a running scenario. Now, the big block is bidirectional power transfer. This really brings us the V2X support. There's a new functional block Q for this. It is developed for -20, but it also supports CHAdeMO. CHAdeMO has been able to do bidirectional power transfer for years. So this also enables CHAdeMO bidirectional power transfer. Now, there's 8 different operation modes. Looks like a lot. Now, if you break them down, the first one is charging only. That's simple. That's the same as what we've been doing for years. So this is normal operation mode, normal charging. This can still be smart charging, so you can still limit the amount of charging speed, but it is not giving energy back. Now, then we have the idle mode. This just means we're not charging anymore. Just go into idle mode where you don't want to charge, you don't want to charge or discharge. The other 6 are, you can almost break them down, and that's what I did here a bit, is there's different sources and different control methods. So there's 3 sources. It's an external, central, or local source. Now, a central source is the CPMS. So that's the CPMS telling via OCPP what kind of power transfer you want to do. So this is the CPMS controlling the charging station directly. Local is the charging station itself. So the charging station measures something, tries to control a certain way how it does bidirectional power transfer. And then you have external, and with external, that's typically an energy management system. So it's a home energy management system, a building energy management system, a site energy management system. If you have a big high power charger site with 10 high power chargers and you have to load balance between them, or take into account bidirectional power transfer inputs from the grid for all these 10 chargers, you might have an on-site energy management system that takes this all into account. Then there's 3 different control types: limit, set point, and frequency. Our limit is what we've been doing with smart charging. We tell a maximum limit. So we basically tell the vehicle, hey, you can't go faster than this, but you're allowed to go slower. You could do the same way the other way around, where you say, hey, this is the fastest you're allowed to discharge, but you could go slower there. So if you want to control the grid by that, it's not really that handy, because you might want to have a certain amount of power feeding back into the grid. Say you want to have 10 amps going back in, but if you set a limit on 10 amps, the vehicle is still fine if it only does 5 or 6 amps, because that's still within the limit. With a set point, we really tell the vehicle, please try to comply with the set point as much as possible. So if we tell the vehicle, hey, please do 10 amps, then the vehicle will try to stay as close to that 10 amps as possible. Now, that is probably the most useful thing you can do with bidirectional power transfer. That does mean that the charging station or the CPMS sending this set point will need to take into account what the vehicle can do. Because if you're telling the vehicle, please provide me back 100 amps AC, that is not possible on AC with any vehicle that I know of. And if you would do DC and you tell a vehicle, hey, please give back 10 kilowatts, but bidirectional it is only possible to do 20 or 30 kilowatts, it can't comply with the set point. And then the last control type is frequency. If you want to do any kind of frequency control to help stabilize the grid, if the frequency is too low or too high on the grid, then you go for one of the frequency control type operation modes, either the local or the central one. So those are the different operation modes. Feels like a lot, but there's a lot of different ways you can do this. I expect a lot to happen. Local load balancing, where you're just balancing between the two, or you do a lot of central set point. It's just a CPMS telling the charge station what it needs to do. Or you have a bigger site, there's an external input coming in, then you do the external set point. The external limit, not that valuable. Central frequency might be too slow to do frequency compensation, so local frequency is probably the most used, where the charge station is measuring locally what the frequency is and then starts to compensate for the frequency. A lot of new operation modes. That comes with a lot of new use cases. So if you look at all the new use cases, there's 12 new use cases here. Now the first one is the V2X authorization. That has nothing to do with the way you control. Up till now, if somebody was authorized to charge, that meant we were selling them energy. So if they were allowed to buy energy, that's fine. But with V2X, you also want to make sure that that driver allows us to buy their energy back. So basically, we're discharging their vehicle, so they need to be willing to do that. You don't want to end up with a driver that went to a high-power charger and then figured out, oh, I wanted to leave in 20 minutes and now my vehicle is less full than it was when I arrived. I was arriving at 60%, now I'm down to 40%. But I wanted to leave with 80%. So you want to authorize for sure to know that the driver allows you to do this. So that's where there's a new authorization method. And then there's a lot of use cases for the different operation modes. So Q2 until Q10 are just the different operation modes and how to handle those in OCPP. Now then there's 11 and 12, which are for offline. How do you handle when a charger goes offline? If you do the bidirectional power transfer, you want control on this. You want to know for sure that the grid isn't changing, and this all has effect if you want to balance the grid. So you need to know how to handle this offline. So what do you do if you go offline during a V2X operations, or why do you resume V2X operation after you've been offline? So there's use cases for that as well. So a lot of your new functionality, but it breaks down to different operation modes and then some additional use cases around that. Now, on top of V2X, if you really look on how grid operators control their grid, they talk in terms of DERs, distributed energy resources. They see the grid on who is using a lot of energy, who's providing a lot of energy, and they want to be able to control this. And for this 15.11.8 added DER control. So they have AC DER control, AC bidirectional power transfer, DER control in the vehicle. If it's DC charging, all of this power control needs to happen in the charging station. So you won't see any 15.11.8 messages because this is then what the charging station needs to do. Now, typically, this is done by the CSO, the grid operator, by using a protocol like 2030.5, ISO 61850, OpenADR. This is how you control big grid loads. You can control active or reactive power. You can influence the power factor that is used on the grid. You can control ramp up rates and ramp down curves just to have these high loads working better with the grids. This is not what you're going to do on an AC home charger. This is typically the stuff that happens on big sites. So if you would be installing 6 micro megawatt chargers on site, and you can all do 750 kilowatts, these are the resources where grid operators want to have better control on how they work on the grid, because these things take power and a lot of power. So you want to do that as good as possible and work with the grid operators as good as possible. And that's where these DER use cases come in. So there's 5 use cases really on how do you do DER control combined with V2X via OCPP. And how you report on things that are happening there. So first thing to implement is V2X, and then following on that is DER control, typically for more high power charges. Now with bidirectional power transfer, as we've seen, you want the driver to authorize, hey, that's fine, I'm fine with doing bidirectional power transfer. But things might change. So you have a truck in a fleet depot. It's parked there for the weekend. You know, I just need it on Monday, so you can use it the entire weekend for bidirectional power transfer. You just need to make sure it's full at the end of the weekend. So on Monday morning, if the truck driver picks up the truck, it needs to be fully charged. But what happens if a emergency happens, another truck broke down, you need this specific truck to leave the depot ASAP. You want to disable bidirectional charging on that and prioritize charging now. Now, there's different ways how this can happen. So either it's locally, so somebody walks on the charge station, selects priority charging. This goes to the CPMS, it changes the schedule and gives the charger the vehicle priority. Or it's this, if you, for example, do local load balancing, where there's a balancing between 2 sockets, or there's a local controller balancing a couple of chargers. You want to say from the back end, hey, can you please prioritize this vehicle on this EVSE? Because this one needs to be charged as fast as possible. A simple use case, you send over a bulletin basically telling, hey, I want to prioritize this charging session, one way or the other, depending on where this input comes from. Now, we've already touched a little bit on energy management systems. OCPP 2.1 already supports energy management systems. You can easily set up external constraints. So if there's an input coming in, if you have a CPMS doing something smart, you want to have some message going back telling the CPMS, hey, there is a local constraint. So somebody set a local limit based on grid constraints, based on available solar, that influences the charging speed. Now for a normal charging session, that's just information to the driver. So if you have an app, you might inform the driver. If somebody calls the contact center, you want to have the contact center being able to explain to the driver why charging is slower. If you have something more advanced where the CPMS is doing some load balancing as well, where there's also external inputs, that external constraints might be a little bit limited. So now we have a better explanation on how to combine an EMS with a charging station, how to combine EMS with a local controller, what happens if the EMS is the local controller, how do you combine different smart charging in the cloud and locally. How do you combine an energy management system with local generation? So if there's local solar generation, how do you take that into account? How do you tell that to the CPMS? So all of that is now part of EMS of OCPP. On top of that, there's a small new use case as well for any smart charging. is dynamic charging profiles. Currently, if you have a charging profile installed on a charging station, you can only replace it. So if something changes, you have to replace the entire charging profile. Now with dynamic charging profiles, you can just temporarily update a profile. So you have a charging profile that says something what you want to do the entire day, but something changed for 1 hour. You can just set a dynamic charging profile and everything continues after that. So it's a small update to be a bit more flexible on changing profiles. And this really becomes interesting if you start doing dynamic tariffs, where you want to take into account the dynamic tariffs and influence charging speeds with that as well. So an additional use case for that as well. That all about smart charging, V2X. So a lot of functionality there. The other big block within OCPP 2.1 is ad-hoc payments and local cost calculation. With OCPP 2.1, we introduced a better way to integrate a payment terminal, but we only basically did the messages. We didn't really explain really well how to operate this correctly. So what we see in the field, there's a lot of companies implementing a payment terminal, but then exactly how to handle this correctly might be different. And that means there's interoperability issues between two different charger brands with two different payment terminals. So if you buy brand A or brand B chargers, they might have implemented this differently. So with OCPP 2.1, we want to standardize a bit more. So how do you authorize with a payment terminal? So this works with both integrated payment terminals, where the payment terminal is integrated in the charging station, directly talking to the charging station itself, and then to the backend. This also works for standalone payment terminals, where the payment terminal is talking to the cloud of the payment provider, then talks back to the, typically via OCPI nowadays, to the CPO, and the CPO does remote start and stops. And this also works for dynamic QR codes. So there's a lot of different ways to do ad-hoc payments, where a driver is able to start charging without needing a subscription, so without needing an RFID, without needing an MSP. How do you handle if you start charging? How do you handle cancellation? How do you handle the settlement? What happens if the settlement is rejected? So a lot of different use cases to make sure all of this works correctly with a payment terminal. On top of that, we have ad hoc payments with QR codes, static or dynamic. AFI nowadays requires in Europe QR codes for for ad hoc payment. That is now also standardized in OCPP, and especially dynamic QR codes can be a pain if you do that in 2.0.1, because there's no standardized way to set these QR codes. And you need to change these all the time. You don't want to send them over. So there's like an algorithm, you just configure certain flags and it will automatically generate new QR codes all the time and show them on the display. Now, the other big block, which might even be the biggest block in OCPP 2.1, is local cost calculation. That means you can do cost calculation on the charging station. So far, we've always tried to keep this outside the charging station because this is way better handled in the cloud. But there are use cases where you would need to do local calculation on the charging station itself. California, for example, requires you to show real-time running costs on a display, like you have on a fuel pump. If you're on a fuel pump, you're filling up the vehicle, you can see on the display the amount of energy that you've put, the amount of fuel that you put in the vehicle and how much that would cost to you. Now you want to do this. They want to do the same with the charging station, which is really nice for the driver, especially on DC fast chargers. You can see the total amount, so you could even say, okay, I stop at 25 euros with charging because I can see it on the display. I just stop in time and just charge for 25 euros instead of for an amount of kilowatt hours until I get to like 80%, whatever I need. But for that to do that real time, you would need cost calculation on the charging station. And there's a California pricing white paper. And that California white paper goes into how to send over the running cost real-time, near real-time via OCPP. So you do an update that was already possible with 2.0.1. You just do a cost update. You just send it over every time there's a transaction event, transaction response. You can do a cost update. You can send them even actively. So you can keep it updated on the display, but that's always more near real-time. So that's every minute, maybe every half a minute, depending on how often you send messages. This is not real time. And there's another corner case where exactly with a payment terminal. If the payment terminal does have its own connection to the backend, which it typically has, and that connection is working, but the connection from the charging station to the CPMS isn't working, the settlement really becomes a problem because you don't know the cost of that transaction. So you have to wait with the settlement before you get the cost in. That means a second transaction can't really happen because that terminal still has a reservation open. With local cost calculation, that would be solved in an offline scenario. So it's a bit of a corner case, but it is a use case that needs to be supported. And the third one, if you really want to do prepaid charging, doesn't happen a lot in Western Europe, but if you go to Eastern Europe, if you go to Africa, if you go to less developed countries, maybe in Asia as well, you see more and more where people are used to doing these kind of services prepaid. So you have a prepaid amount on your card. If that's empty, you want to stop. Now, you could get near real time with OCPP where you would just calculate the cost every minute and just send a stop, but that wouldn't be perfect. You would always stop a little bit in front. Now with local cost calculation, you could do, I want to just charge for 20 euros. You set a maximum 20 euros, then it's done. It will stop exactly at that. But for that, you need tariffs. In the charge station, you need to be able to calculate running cost. And there's a couple of use cases for this. You need to be able to set the default tariff. So if an Ad-hoc charging session is happening with a payment terminal, you want to use a default tariff. So that's a tariff used for everybody. Now, more advanced, if somebody has a subscription with a CPO, with an MSP, that might be different from the default tariff. Like with a petrol station, if you end up at a petrol station, use a bank card, you just get the normal price of a petrol station. If you have a fuel card, there might be a different price there. You won't even see that on the display. With this, you might see your own cost on the display. So you really see your cost, what you would pay, which isn't even possible with the fuel pump at the moment. That means how do you receive the user tariff? How do you handle that? That is taken care of in OCPP. Now, there's some management there. You can get tariffs. You can clear tariffs. You could even change the tariff in a running transaction. Is that allowed? That depends on your legislation. There's a lot of countries that won't allow you to change the tariff on an ongoing transaction. As a driver, you've accepted the tariff before you start charging. You can't change it while that thing is happening. So that is also, it is possible to take into account if this is allowed in your country. And then the last thing is, how do you report on this? If you do a transaction event, transaction ended, you want to report on the total cost, so that what kind of details are in there, total cost, energy cost, time cost, one-time fees, taxes, all of that broken down into the transaction event is described in I-12. So a lot of use cases for doing local cost calculation. Now that's for EVerest will be a big block. We will need to build a billing engine that can do this embedded. I've worked at Ericsson. We had a big team developing the Ericsson billing engine. It's a huge task to do this correctly. You need to round this to the smallest amounts. You can't make rounding errors. This needs to be so correct. So it's quite a big block to do correctly. And I would advise everybody that is going to implement local cost calculation, please talk to us. Please talk to the EVerest community. Let's work together. Let's build just one good open source engine that everybody in the world can use and provide input to and debug, because this is going to be a big block where it would be a waste of time if everybody starts developing their own. With local cost calculation, we also get the capability to do, as I already said, fixed cost. So you're now able to do local cost calculation on an amount and stop charging at that point. So there's new use cases to support this. How do you authorize a prepaid card? How do you start a tariff with fixed cost, fixed energy or fixed time? But also remote start with a fixed cost, energy or time. Now, energy and time is simple because that's easy to measure in a charge station. Cost will heavily rely on the local cost calculation. So we really start adding now functionality to make prepaid charging sessions viable. Then we get to some miscellaneous use cases. Some other small use cases that don't really fit in a bigger group. One is B13, reset with an ongoing transaction and resume transaction. This is really for fleet use cases. This isn't really for public charging. If you have a public charging station, that charging station reboots or power cycles, you can't be sure that the same vehicle is still connected. You don't know for sure that that vehicle is there, but you might. But typically for fleet scenarios, if trucks are charging overnight and there was a power failure for half an hour and power comes back online, you don't want to have somebody go on site and start all the charging sessions again. You might just want to resume charging when power comes back online, because this is depot, this is vehicles, for anyhow, there's no payment is completely handled differently. So B13 and E17 really focus on how do you handle this with power cycles, with resets, that kind of stuff. Another big block is A18 battery swapping. I either expect this to either be broken down in a couple of use cases or maybe it ends up in a white paper. Now it's one use case for battery swapping. This adds support for automatic battery swapping stations, manual battery swapping stations. Take, for example, NEO, but especially in India, Bangladesh, we see a lot of 2 and 3 wheelers that becoming electric nowadays. And these use battery swapping a lot. They take, you go to a battery swapping station, you take your own battery, put it in, you take out a new battery, put it in your vehicle, and you drive away. You do need to pay for it. You need an authorization for it. You do need payment method for it. And the batteries need to be charged. So it feels very similar to OCPP, but it is a bit different. So we can reuse a lot from OCPP to make battery swapping possible. So not sure if this ends up in the spec or will be a separate white paper, but it will become possible with OCPP 2.1 anyhow. Then something new in OCPP 2.1 that goes a little bit deeper. So this is really for the people that don't know the RPC framework a bit better. Up so far, we only had, which is on the left here, we had call and call result. So if the charging station had something to report, it would do a call, so basically a request to the CPMS, meter value, notify event for device model stuff, and had to wait for the call result, like, hey, I've processed this now, I'm done. This was a bit slow because we could only do one call and had to always wait for the answer to come back. Also means if there was a queue that needed to be emptied, that we needed to take this into account. And we saw bigger networks that were starting to struggle. Especially if you want to debug some stuff, you have high volume monitors open in device monitoring. You just want to have data. You don't want to have to confirm this. This is not that important. So how can we simplify this? So we took a look at what does TCP/IP do. TCP/IP has the same call and result, but you also have UDP, which is like you just send and there's no response. It's a minimum amount of data, so we try to keep the packets as small as possible, and you just send out data. So that means that on the RPC framework, there is a new call message type, which is called send, and it doesn't have a send result. There's no send error. It's just a message. It goes to the CPMS, done. And it can be sent quickly. Now, the content of that is really small. It just has an ID. So which stream is it? If there are more data, and then there's the data, and the data is just a timestamp and a value. And you can have multiple of these values inside the same event stream message. Now, there's a couple of use cases surrounding this. So how does this work? The CPMS is in control. So if the charging stations support event streams and the CPMS wants to monitor something on a high frequency, they can set up an event stream. So you take one variable that is monitorable and supports event stream, and you just set the frequency of the event stream. You also set the unique ID, which identifies all the events coming back in. Now, you can also manage this, so you can get which event streams are there. You can close one. You can make changes to the event streams. You can change, for example, the frequency. And then N15 defines how to what these event streams look like if you send a message. Now, there's a couple of messages surrounding this. It's the notify event stream itself. So this is really the thing that does the send command, and the others are opening, getting, adjusting, and closing. That's managing the different event streams that are in the charging station. And lastly, we also on RPC framework level, we get a call result error. This is seen also on the previous slide already. Up so far, we had call, and if everything went okay, call result. If something was wrong in the charging station, or in the other way around, if you would send something to the CPMS, you would get back a call error. Just saying, hey, you sent me this message, but there was an error. Now, that was all well and fine. If you, for example, did an authorized request, and I got back an authorized response, if I do the authorized request that is wrong, I get a call error back on the response. The problem is if the authorized response is wrong, I can't really tell back like, yeah, you're sending me something here that I can't handle the response. There wasn't a way of telling that. Now with OCPP 2.1, we introduced call result error, and this gives a capability for the receiving. So if you do the request, you get back the response, and there's a problem with the response, you can go call result error, telling the other side like, hey, you sent me a response to this, but I couldn't process this. So more also for debugging, new message just to make it better to support. And there's corner cases now in OCPP 2.1 where this becomes really useful. Something is wrong with the call result, that because we need the call result information a bit more, where we're able to report errors on this. And this brings us to the end. So this is all what's new in OCPP 2.1. A lot of new use cases, a lot of new functional blocks even. Biggest blocks, V2X support with DER support and the local cost calculation combined with Ad-hoc payments. And then we have 2 new extensions on the RPC framework. All of this new functionality is optional. If you want to do a core 2.1 implementation, it's very similar to a 2.0.1 implementation. So that shouldn't block you from doing this. We in the EVerest community started working on 2.1. We need to do a little bit of architectural work to better include a third protocol version, because we do OCPP 1.6 and 2.0.1 at the moment. If you want to learn more about EVerest, please look at the show notes below. Thanks for your attention, and see you in another video.